Hello students, this is Dr. Bhavani Regmi and in Survey of Chemistry class first. So today we are continuing on our chapter 4. In our chapter 4 we are talking all about the covalent compounds. We learned the V-shaped R theory to predict the shape of the covalent compounds. Today's lecture will be on the continuation of V-shaped R theory, applying that in order to know the polarity of the molecule. Okay, so when two atoms share electrons, they form the covalent compound. We all know that, right? But are these shared electron in the bond, in that shared pair bond, are they attracted to the both of the nucleus of both element equally or not, right? That question will be answered if we know about the electronegativity nature of the element. Okay, so let's learn about what is electronegativity. What is the trend of electronegativity in the periodic table? Then we can say whether the bond forms in the sharing of electrons, whether that sharing is remain equally or remain unequal. Okay, so let me define you the electronegativity nature. The electronegativity, it is the measure of the atom's attraction towards the electron that is used in the covalent bond. Okay, so in a compound, so two elements share their electrons, make a compound, right? They do have a bond between them. Now, those electrons between them, will they spend equal time or equally among those bonds, among those elements? Or one of the partner will be more possessive in nature and let the electron spend more time around itself. Right? Electrons are the electron cloud. They are revolving around the nucleus, right? So that gives us the idea. So electronegativity tells us how much a particular atom wants that electron, how possessive is that element in the compound. Okay, generally the electronegativity is taken as a guidelines to indicate whether the electrons in the bond are equally shared or unequally shared. The electronegativity value is generally given from the range of 0 to 4. Okay, so in periodic table we are mostly more concerned with the main group elements. So the numbers given here underneath each element is their electronegativity value. Higher the value, it means it is more possessive in the nature. So here right away you can see fluorine atom has the electronegativity value 4. It means the fluorine atom is the most possessive in the nature. Okay, the other atoms, like on the metal side, we have lower values, right? So in the periodic table, the electronegativity value increases as we move from left to right. Okay, or as we move from bottom to the top on the column, the electronegativity value also rise up. So now let's use the electronegativity value to talk about the bonds. Okay, so if they're identical, okay, whenever the two atoms that are identical, okay, or if we have the two atoms that have the similar electronegativity values, okay, in that case they will share the electrons equally. Okay, no one is more possessive than other, right? If you have chlorine molecule, then both chlorine atoms of the molecule will have that shared pair electron shared equally among them. So we have like electronegativity value of chlorine is 3.5 minus 3.5 is 0, right? So the difference H0 means it is a non-polar covalent bond. The bond is equally shared, so we call it non-polar. Right? When the sharing of this electron between the two bonded atoms is not equal, we call them polar bond. Polar bond means one of the side is more deficient in electron cloud, the other side is more rich in electron cloud. Okay, for example, if I have a molecule of hydrogen fluoride, okay, and I just told you that fluorine is the element that is very possessive in the nature. It means that share pair electron, okay, it shares the electron with hydrogen, but it is more possessive in the nature, so it attracts that electron more towards itself. So we saw this with the arrow, where the head of the arrow means the electron is more towards the fluorine side, and the bottom of the arrow, the other end, is crossed out, means it is positive side, poor in electron, right? Rich in electron means negative, delta negative sign. Poor in electron means delta positive side. So in HF molecule, this bond between them is not shared equally. So we have a polar bond here. Okay, so we can use the values of electronegativity to tell whether the bond is polar or non-polar. Okay, so how do we use that information? Yes, for our class, we have that here. I talk about it. That if the electronegativity difference between the two partners is less than 0.5 unit, we call them non-polar bond. Okay, non-polar bond means we understand the sharing is done equally. The electrons are shared equally, okay, among them. And now, if the electronegativity difference is in between 0.5 to 1.9 units, then we have a polarity there, right? Polarity means we do have something with positive side and something with negative side, right? We have polarization occurring there. So we have a polar covalent. Okay, in that case, electrons are shared, that's good, but they are shared unequally. Okay, some of them are pulled more towards the more possessive element. So the element which is more possessive in nature, who has higher electronegativity value, we call them more electronegative element. So fluorine is the most electronegative element in the periodic table. Okay, because it has the highest value of electronegativity. So we can see here, if the difference between the two electronegativity value of two elements we are talking about in a molecule, if that is greater than 1.9, okay, there is a huge difference on their electronegativity, it means that we are talking about a special case, and this case is known as ionic compound, right? We do have the ionic bonding occurring that place. It is no more covalent, and the ionic means we do have transfer of electron. We do the metals are less electronegative element. They transfer the electron, and the non-metals receive those electrons. Right? So just looking on the electronegativity difference, we can tell whether the bond is covalent or ionic. If it is covalent, we can tell whether the bond is polar or non-polar. Okay, so let's use this information to figure out this question. Let's say we need to know whether the bond between carbon and oxygen is polar or not. How do we know that? We need to know these values. These values will be provided in your exam. Okay, you are not supposed to memorize this. I just remember that fluorine is 4. I don't remember others. So we get this table and we use that given values to calculate. So electronegativity difference between carbon and oxygen means Oxygen has 3.5, carbon has 2.5. Always subtract the smaller number from the larger number. So we have difference of 1. If the electronegativity difference is 1, then we are in the category over here. It is between this, right? So we have the polar covalent bond. It means the bond between carbon and oxygen, it is polar one. Okay, let's say you have another question. Is the bond between the carbon and nitrogen polar? Let's say that is the question. Okay, again, you have nitrogen 3, you have carbon 2.5, the difference of them is 0.5. The 0.5 is also on the polar covalent, right? So this is also polar. Now, if the question is among these, who is more polar, CO or Cn? Then you choose CO is the more polar because the electronegativity difference here is 1 versus 0.5 in the Cn. So more higher the difference in the electronegativity, more polar will be the compound. More polar will be the bond. Sorry, more polar is the bond. Okay, so this slide we learn about how to use the electronegativity value to determine whether the bond is polar or not. Okay, is that clear? Okay, now let's move on. Using that information. Okay, now you might see the questions like, what about the molecule? Are the molecule polar or not? If the question is such a way, then first we need to look whether the bonds are polar or not. After that, we have to look on the shape of the molecule, and combining all these answers, we have to come up whether the molecule is polar or not. Okay, so let's see. Whether a molecule is polar or not, it depends on the polarity of individual bonds. That is correct. As well as it depends on the overall shape of molecule. Something we learned in earlier video, right? How to determine the shape. We need to apply that V-shape R theory to know the shape of molecule. And then we analyze whether that molecule is polar or not. Okay, generally, if we have no polar bonds, okay, if we do not have any polar bonds, then the molecule is non-polar. Okay, because there is no segregation, there is no pluses and minuses there, no charge separation, everywhere it is equally shared, right? There are no polar bond, means the molecule is non-polar, right? For example, the methane molecule, if I have carbon and I have 4 hydrogen around it, okay, the electronegativity difference of carbon and hydrogen, you just need to take any one hydrogen and the carbon, okay, do not take all 4 of them. So if you want to know the electronegativity difference of carbon and hydrogen, then look on the table that we have in the earlier slide. Carbon is 2.5, hydrogen is 2.1, the difference is 0.4. And if the difference is 0.4, it is a non-polar bond, right? And whenever we have non-polar bond, all these bonds are non-polar, we have a non-polar molecule. Okay, so that's the example. Now, if we have molecule that has some individual bonds, but they do cancel, in that case also, we will end up making non-polar molecule. What does it mean? Let me show you with an example here. Okay, I have boron trifluoride, okay, BF3 molecule. If you write the Lewis structure, if you draw the Lewis structure, you will have boron in the center, 3 fluorine on the trigonal planar structure, right? The V-shape R theory tells us 3 electron domain, means you have to keep them as 120 degree apart, right? 120 degree apart. So they are at trigonal planar shape. And now if you have those, now you check whether the bonds are polar or not. The fluorine is 4.0, boron is 2.0. Okay, if you look on the table earlier slide. So the difference here, the delta En, right? Delta means the difference. The difference in the electronegativity of the fluorine and boron here is 2. Okay, 2. That means it is an ionic bond, right? It is a polar bond. It is an ionic one. But what you will see is all these bonds over here, they are facing away from the boron towards the fluorine, and they are at perfect 120-degree apart. So what is happening here is the dipoles, means you see how the direction of the polarity is going. It is a vector. Okay, dipole is a vector quantity and they cancel each other. Okay, so when they cancel each other, we do not have net dipole here, so the molecule is a non-polar molecule. Okay, so only talking about the bonds will not tell us the complete picture about the polarity of molecule. Here the bonds were polar, but the molecule is non-polar because individual bond dipole cancel each other. Okay, whenever the molecule is symmetrical, okay, like trigonal planar here, okay, and all the outer atoms are the identical one, they are pulling the shared pair electron with the same force. The dipole moments are the forces that are pulling the shared pair electron, and the forces are acting in opposite direction to each other, right? So between these two forces, you will have a resultant force over here, and that resultant force is directly opposite of this force going on here. Okay, a little bit physics here. So these forces acting in opposite direction, so they cancel each other. So as a result, we have a non-polar molecule. Now let's see the condition where we will get a polar condition. Okay, generally if we have only one polar bond, let's see here with an example, right? We have only one polar bond, the oxygen is more electronegative than carbon and it is sharing that shared pair electron, it is pulling more towards itself. When it is pulling more, we have one polar bond, right? And it is a polar molecule. If you want to go by the number, the oxygen is 3.5, carbon is 2.5, the difference is 1. If the difference is 1, we have a polar bond here. So we have a one polar bond, it means we have polar molecule, right? Now, if we have multiple polar bonds and they are not cancelling, then we get a polar molecule. For example, here the ammonia molecule. Okay, if you see each bond are polar, nitrogen has electronegativity 3.0, hydrogen is 2.1, so the difference is 0.9 here. Okay, but nitrogen is the one that is pulling, right? It is the one who is more electronegative and it is pulling electron pair from the three sides and it is adding up, it is accumulating on the nitrogen. So there is a polarity. All the dipoles, they are reinforcing, they are not cancelling. So we have three polar bonds, they are adding up, so we have here a polar molecule. Let's see one more example. We have H2CL2. Again, we have two polar bonds here. So between carbon and chlorine, we have polar. This is the polar one. But carbon hydrogen is not polar, right? This carbon hydrogen is not polar. And these two polar bonds are not facing opposite direction. They are giving a net resultant dipole in between them. So two dipoles are adding up. They are not opposite, right? They are adding up. So we have a polar molecule. Okay, so that is how we figure out that even how a molecule will be polar. So yeah, in this scenario, let's say if we have, instead of 2 hydrogen, okay, let's say if we had all of the outer atoms in the tetrahedral fashion, let's say if they are chlorine atom, then what will happen? Okay, I'm giving you one extra example here. Okay, so here what is happening, each of the chlorine is pulling the shared pair electron because chlorine is more electronegative in nature. Okay, the electronegativity value of chlorine is, I'm looking on the book right now, it's 3.0 and carbon is 2.5. So we have 0.5 difference in them, right? So these bonds are polar. If the question is, are these bonds polar? The answer is yes, the bonds are polar. If the question is this molecule polar? Then we have to look on the shape also. Okay, on the shape, what we are observing here are, we have 4 dipoles, right? All these pulling, the 4 dipoles are in the direction of 4 vertex of the tetrahedron, right? This is a symmetrical structure. The perfect tetrahedron, the perfect trigonal planar, these are the symmetrical structure. Okay, the perfect linear, when they are facing opposite, they are the perfect symmetrical molecule. If they are symmetrical molecule, if the dipoles are facing opposite to each other, then all of them will cancel each other's force, right? So as a result, we do have a non-polar molecule here because the dipoles cancel out. Okay, I guess you have understood how to look on the bonds and then how to look on the shape of the molecule to talk about the overall molecule. Okay, even the bonds are polar. In some cases, the molecule is non-polar, right? Some cases, the bonds are polar. They add up the dipoles. The molecule becomes polar, right? So that is how we have to analyze, looking closely to each of them. Okay, so that is I guess that is the last slide of our chapter 4. Okay, so we use the V-shape R theory, the shape of the molecule, the electronegativity difference as a guideline to talk about the polarity of bond. And when we gather these information together, we could talk about whether the molecule is polar or non-polar in nature. Okay, so that concludes our chapter 4. Thank you.